Hi friends, we are going into the class 5 of module 4 automatic generation control, and in this class we are going to study how to make the generator load model. That is the third model. We have already studied how to make the model for a turbine speed governing system. Then we studied turbine system model, and third one we are going into generator load model. So in this generator load model we are going to find out or we are going to model the system first by finding out what is the increment in the power input to the generator load system with a change in frequency. With a change in frequency, what is the increment in the power input? So how can we represent the change in the power input? Change in the power input can be represented as it is a generator load model, it can be represented as delta Pg minus delta Pd. Delta Pg means the increment in the generated power and minus delta Pd means the increment in the load. Okay, now this is accounted in two ways. This increment in power input is accounted in two ways. The increment in the generated power is accounted by the rate of increase in the stored kinetic energy in the generator rotor. Okay, how it is being changed with respect to frequency. Okay, and the second one, that is the change in the load demand, that means minus delta Pd, it is accounted as the rate of change of load with respect to frequency. Okay, now we are going to the first one, that is the rate of increase in the stored kinetic energy with respect to frequency. So first we have to go through what is the actual kinetic energy for a particular frequency f0. Okay, so at a particular frequency f0, the stored energy is WKE0 is equal to H into PR, where H is the inertia constant and PR is the kilowatt rating of the turbo generator. Okay, so together the kinetic energy is expressed in kilowatt seconds or kilojoules. Okay, this is the kinetic energy for a particular frequency f0. But if there is a change in frequency, that is why we started with the rate of increase in the stored kinetic energy in the generator rotor with respect to frequency. What is the rate of increase with respect to frequency? So we are going to make a small change, that is delta f. Okay, if the frequency is changing by a small value delta f, what happens? The frequency becomes f0 plus delta f. Okay, now we know that the kinetic energy is proportional to f square. So WKE, that is the kinetic energy at f0 plus delta f, and WKE naught, we are taking the proportion of it or ratio of it, then we will be getting f0 plus delta f divided by f0 the whole square. Okay, from which we can find out what is WKE. So WKE is equal to, by substituting this one to the right hand side, you will be obtaining this equation. Okay, now what is WKE0? WKE0 is H into PR. So we can represent this one here. So it becomes H into PR into, we are expanding this term, so it becomes like this, and this delta f square is very small. As delta f is very small, we can consider delta f square negligible, so we can neglect that term. So the remaining term becomes HPR into 1 plus 2 delta f divided by f0. Okay, now we can totally write the rate of change in kinetic energy with respect to this change in frequency is d by dt of WKE is equal to, we are taking the differential of this one. So the differential of 1 becomes 0. So the remaining terms are 2 into HPR divided by F0 d by dt of delta F. Okay, so this is the rate of change in kinetic energy with respect to the frequency. With the change in frequency. Now second one is the change in load demand with respect to frequency. So as the frequency is changing, the load will be also changing. Why? Because it is very sensitive to speed. Speed means frequency itself. The change in frequency means it will be same as this change in speed. So the motor load is normally sensitive to the speed. So there will be surely a change. And this is actually a proportional change. If speed is increasing, then the load will be also increasing. So we can take the rate of change of load with respect to frequency as almost a constant. Okay, it is almost changing linearly. So dou PD by dou F can be considered as a constant. And for small changes, we can represent this one as dou PD by dou F into delta F is equal to, this one is a constant, so we can represent it as B delta F. Okay, and here we have to consider that this this dou PD by dou F is a constant B. Okay, and PD means the load change and dou F means the change in frequency. Okay, where B is a constant, and normally B is predominantly positive for the load. If it is predominantly a load, motor load, then we can consider the B value as a positive value. Okay, now we are going to combine these two equations, which are the delta Pg minus delta Pd. That means delta Pg means the change in the increment in the power generated, and this is the increment in the load. So these two are equated with the rate of change of kinetic energy with respect to frequency and the rate of change in load with respect to frequency. This one for accounting, this one and this one. Okay, so dividing by throughout by PR, we are going to divide the whole equation using PR. PR means the rated power. This equation completely is divided by PR. So what will happen? If we are dividing with the rated value, we will get its per unit value. So delta Pg divided by PR means it will give you the per unit value. Delta PD by PR, it will give you the rated delta PD, per unit value. Then similarly here PR by PR will give you, this will be cancelled out. Then the remaining in this term, we will be dividing with PR. What happens to this one? Even though it is a constant, this B is actually dou PD by dou F. So if you are dividing with PR, what happens is this dou PD by PR, it becomes, that is increment in the load divided by rated power. So actually this one also becomes a per unit value. Even though it is a constant, it is actually a per unit value. Okay, so that is why we are representing it as B per unit into delta F. Okay, now we are going to take the Laplace transform. So delta F of S, from this equation, we are first making it into the Laplace transform. So what will be the equation? Delta Pg of S plus delta Pd of S plus 2h by F naught into this d by dt becomes S into delta F of S plus B into delta F of S. And from this, we are going to find out what is delta F of S. And by doing the calculations, you will be obtaining as delta F of S is equal to, delta F of S will be equal to delta Pg of S minus delta Pd of S divided by B plus 2h by F0 into S. And from this equation, we are going to take B outside. So what will we get? B into 1 plus 2h by F naught into B into S. Okay, and using this Laplace transform, we are going to make the transfer function model. So the transfer function model will be delta F of S is equal to, okay, this delta F of S is equal to this much value into, so this becomes the input side, this is the output side, this is the input section, and this will be the transfer function. So the transfer function will be Kps divided by 1 plus Tps into S, where Kps is, we have already taken B outside and we are writing it here. So it becomes, Kps becomes 1 by B, and in the denominator you will be having Tps, that is the time constant, as 2h by Bf0. Okay, so we have found out the transfer function model, and we can now represent the block diagram using this representation, that is delta Pg of S, that is having a positive sign. Delta Pd of S means it is having a minus sign. So delta Pg minus delta Pd is the input and delta F of S is the output. Okay, and the transfer function is Kps divided by 1 plus Tps into S. So this is the block diagram representation of the generator load model. Hope you understood. Thank you. We will continue in the next class.